This is our presentation of life cycle assessment of 3D printed buildings, presented by Josh Waddell, Jimmy Yashar, Charles Mitchell, and Kayla Griffin for CM7303 life cycle assessment with Dr. Pang. I hope you enjoy.
The major differences between conventional and 3D printed buildings. The LC phases of concrete and 3D printing have similar steps. Both assess environmental impact across a product's life from cradle to gate, sometimes to grave. 3D printing is still relatively new, and there is not as much research, like conventional construction, on the use and end of life. Conventional versus 3D printing and design. The design for efficiency, 3D printing allows for built-in features like channels and wiring or plumbing during the printing process. This saves on time and labor. Also, 3D printing can do more intricate details at half the price, whereas traditional construction methods cost more and have an increase in time and labor. I spent a good bit of time talking about the design phase because it is one of the highest costs in construction waste. Also, 3D printing shows failed prints and test prints being the highest waste percentages. Failed prints can be due to design flaws, operator error, or equipment failure. Raw material extraction, processing, and manufacturing. The extraction and processing of these raw materials require energy and can cause air, dust, noise, and water pollution. It generates significant waste from cutoffs and unused materials. 8% of the world's carbon dioxide emissions come from cement manufacturing. The elementary flows of concrete need a considerable amount of water, and the discharge of the wastewater can harm nearby ecosystems. Intermediate flows, concrete generates waste during the production process and the unused concrete and waste from cleaning equipment. Many 3D companies have their own proprietary blend. As you can see below, these are multiple 3D printing companies, and they don't specify what's in the blend, but some of them specify the environmental impacts and how beneficial their proprietary blend is. 3D printing eliminates the need for formwork, potentially reducing construction phase energy use. The building's carbon footprint can be lowered about 70%. It also requires less material and energy to construct and can be more environmentally friendly. And also, it is a higher upfront cost, but can save costs in the long run due to increased efficiency. There's few primary data resources found for 3D printing. Secondary resources like journals and reports were used. Since there is no universal standard for cost calculation for site assembly, each project transportation cost can make it difficult to quantify. Conventional. Energy consumption. Transportation involves transporting numerous materials to the building site relying on fossil fuels. This contributes to GHG and local air pollution. 3D printing can potentially be done on site, reducing multiple material transportation costs, which lowers fossil fuel consumption. Transporting the printer to an on-site project can be 5 to 20% of the total cost of the printer. This does contribute to GHG and local air pollution. Conventional. Durability and maintenance. All depends on the quality of the product. Durable concrete buildings that last for decades require fewer replacements, which associates decreasing environmental burdens. Egocentric restoration. This highlights the focus on personal preference over broader concerns. 3D printing. Repair and maintenance. 3D printed product can be easily repaired or have replacement parts printed on demand. It can extend its lifespan and reduce the environmental impact compared to needing a complete replacement. At the end of the life, concrete can be used in different ways. Either it can be recycled to create replacement gravel and new concrete mixes or for road-based layers, or can be reused whole, for example, in seawalls or erosion control. The demolition, however, requires energy-intensive machinery and can generate significant dust and debris. 3D printing is such a new concept. The environmental impact of their demolition and potential for recycling the materials is not well understood. However, if it's traditional concrete, it could be the same as what we just spoke about. If it's bio-based materials like sawdust and bioresins, these houses can be entirely recycled at the end of their lifespan. This picture is a great capture on the different environmental impacts concrete can create. Concrete can affect water runoff, bring a high pH level to the soil, which can kill microbial activity, pollute drinking water, and produce air pollution from dust. Depending on the material used, 3D printing can have similar environmental impacts. It all boils down to the type of concrete mixture used. A study was conducted and showed OPC mixtures 3D printing performs better due to its lower cement content and use of waste materials as cement replacement. The study concluded that 3D printing concrete mixture was not as strong as conventional concrete mixture. If one were to achieve the same strength, 3D printed components need to use higher grade, which results in higher environmental burdens. Also, environmental benefit increases with the level of building complexity and decreases with the reuse times of the formwork.
LCA study goals and scope definition. LCA has become an important part of the individual and companies' policies to reduce greenhouse gases for the environment. Most people understand and realize that construction industry plays a big role in environment. It is critical for building professionals to understand why and how to use LCA in their works. Constructing a building and using it for many years produce long-lasting impact on human health and the environment. Life cycle assessment is the rapidly evolving science of eliminating these impacted in terms of their quality, severity, and duration. A building generates environment impact through its life cycle. The various stages of the typical life cycle as defined in LCA are A. The production and construction stages, B. The use stage, C. The end of life stages, and lastly the D. Externalized impact beyond the system boundary. There are many possible reasons for conducting an LCA of a building. The broad goal is usually to understand a building's environmental impact, but it is helpful to identify a more specific goals. LCA study goals and scope help us, number one, to assist in decision making, to compare design options, to test options between multiple suppliers of similar product with different environmental impacts, to evaluate a building, to identify the largest contributor to the total environmental impact. Number two, declare performance with respect to legal requirement to comply with the emerging regulation. Number three, document environmental performance to achieve green building rating points, which commonly require comparing a proposed design to a reference building. Number four, support for policy development to compare the impact of different development options for planning and zoning requirements.
My name is Charles Mitchell, and I am presenting the life stages and parameters of 3D printed buildings. Let's look at the life stages of traditional buildings. They begin in the production of raw materials and transportation to the job site. During the construction process, they are assembled and finished for the operation and occupancy stage. After a building can no longer serve its purpose, the end of life stage, it is deconstructed and disposed of, usually to be replaced by another traditionally built building. The reuse of building materials is much lower than what may be possible with 3D printed buildings. With 3D printed buildings, the life stages are similar. During production, the raw materials are gathered according to the design's needs. Often they can be transported directly to the job site for the construction phase. There may be certain assemblies that need to be printed under controlled conditions off-site and then transported to the job site. During the construction stage, the structure is printed according to the parameters needed for printing speed, layer thickness, flow rate, and environmental conditions. As part of the construction stage, the printed structure will need to be finished according to the desired specs on curing methods, surface finishes, and assembly of pre-printed parts. After the structure is complete, the rest of the aesthetics will be completed. Once complete, the building moves into the occupancy and operations stage, where it can be maintained and updated as needed until the ends of its service life. With 3D buildings, the deconstruction process should become the production process for the next building. The raw materials used in printing should be reincorporated into the next building's life stages, continuing the usefulness of the initial raw material production.
My name is Josh Waddell, and I will be presenting the parameters that influence the 3D printed building sustainability impacts. Material selection. The choice of materials used in 3D printing can have a significant impact on sustainability. Selecting eco-friendly and recyclable materials can reduce the environmental footprint of the printing process. Eco-friendly materials. Choosing biodegradable, recycled, or bio-based materials for 3D printing can reduce the environmental impact of the printing process. Recyclability. Selecting materials that are easily recyclable and can be used in the printing process or other applications can help minimize waste generation. Energy consumption. The energy consumption of 3D printers during the printing process can contribute to the overall sustainability impacts. Using energy-efficient printers and optimizing printing parameters can help reduce energy consumption. Energy-efficient printers. Investing in energy-efficient 3D printers and using them optimally can reduce the electricity consumption during printing. Print parameter optimization. Adjusting printing parameters such as layer thickness, infill density, and print speed can help optimize the printing process and reduce energy usage. Printing speed and efficiency. The speed and efficiency of the printing process can influence sustainability impacts. Faster printing speeds and optimized printing parameters can reduce the overall resource consumption and waste generation. Fast printing speed. Fast printing speeds can reduce the overall time and energy required for printing, making the process more efficient. Optimized designs. Designing parts with efficient geometries and support structures can improve printing efficiency and minimize material waste. Waste generation. The amount of waste generated during the 3D printing process, including support structures and failed prints, can affect sustainability. Minimizing waste generation through efficient design and material usage is important for sustainability. Support structure optimization. Designing parts with minimal or easily removable support structures can reduce waste generation. Failed print recycling. Implementing processes to recycle failed prints and unused materials can minimize waste and promote a circular economy approach. Post-processing and finishing. The post-processing and finishing steps after printing, such as cleaning and surface treatment, can also impact sustainability. Using environmentally friendly post-processing methods can help reduce the overall environmental impact. Environmentally friendly method. Using non-toxic and eco-friendly post-processing techniques such as water-based cleaning solutions and biodegradable coatings can reduce environmental impact. Energy efficient finishing. Opting for energy efficient curing and finishing methods can further enhance sustainability. Transportation and logistics. The transportation of materials, products, and components in the 3D printing supply chain can contribute to sustainability impacts. Optimal logistics planning and local production can help reduce the transportation-related emissions. Localized production. Setting up local manufacturing facilities and utilizing distributed manufacturing networks can reduce the need for long-distance transportation of materials and products. Sustainable packaging. Using eco-friendly packaging materials and optimizing packaging design can minimize environmental impact during transportation. End-of-life considerations. Considering the end of life of 3D printed products and materials is crucial for sustainability. Designing for disassembly, recycling, and reuse can extend the life cycle of printed parts and reduce waste. Design for disassembly. Designing products for easy disassembly and components reuse can extend the life cycle of 3D printed parts. Material recycling. Implementing recycling programs for used 3D printed materials can promote a closed-loop system and reduce waste sent to landfills. This concludes the parameters. By considering these parameters and implementing sustainability practices throughout the 3D printing process, businesses and individuals can minimize the environmental impact of 3D printing and promote more sustainable manufacturing practices.
Good morning, my name is Yashar, and I'm going to be discussing the opportunity and challenges regarding LCA of 3D printed buildings. The 3D printed building technology is a new technology that uses software system for design purposes. It plays a major role for the better design that in return reduce electrical usage and more efficient unit processes to reduce CO2 emission. Like any other system, it has advantages and disadvantages. Let's look at the opportunity regarding the LCA of 3D printed building. Well-designed buildings, systems, and control strategies can improve comfort levels, increase reliability, and reduce costs by optimizing use of component technology. Advanced software, a BIM, that models buildings as integrated systems provide a powerful set of tools for ensuring effective building design and operation. These systems can predict building energy use given a description of its geometry, construction, systems, operation, occupancy, and local weather condition. Building energy modeling allows architects, engineers, and energy consultants to design a building envelope, systems, and operation schemes to match its anticipated use profile and local conditions and to maximize energy efficiency or return on investment while subject to constraints such as first costs, innovations in the process of construction itself, such as greater use of modular component that could minimize air leaks and other problems associated with site construction might make this easier to accomplish. Let's look at the challenges regarding the LCA of 3D printed building. Number one, the most small to medium-sized builders do not use the 3D or BIM software due to the cost. Number two, operability is another factor. It is important that the contractors and the subcontractors are able to have access to the program. Number 3, accountability is another factor that plays an important role because of the legal matters. Number 4, communication and type of the contract like design, build, GMP, that is a guarantee maximum price, IPP, and design, bid, and build, and more. In conclusion, 3D printed buildings are important since it helps to reduce the energy consumption as well as emission gases that are harmful to the environment and human health. Construction plays a huge impact on environment from cradle to grave, and understanding the processes will help stakeholders to contribute to reduce greenhouse gases as well as safeguarding human health.